Hello. So this is maybe a surprise for you guys, but we have been planning this for a little bit. We being myself and Philip. So this is going to be basically an attempt to do sort of a more casual podcast style discussion about. We're going to start with classic Sudoku, although we're not going to necessarily limit ourselves to classic Sudoku. But there's a lot to explore just in classic, so that's what we're going to assume to be doing for now. And that's certainly what this episode's about. So if you remember the last classic Sudoku video I made, I talked about a technique called alternating inference chains in specifically continuous nice loops. And that used a new nomenclature and the concept of links. And I figured I could have a discussion with Philip about weak links, strong links, and their applications, and we could record that. And hopefully everyone can benefit from Philip's knowledge here. So basically, Philip's the expert here, and I'm just going to be asking him questions as we go along. I'm sure he'll be teaching me things I didn't already know, so that will be awesome. And we have some example puzzles we'll be going through, although not necessarily solving to the fullest, just some example situations. And so, Philip, do you want to introduce yourself real quick?
Hi, I'm Philip Newman. I think most people probably know me if you're watching David's channel, but I set mostly classic Sudoku, but also some variants as well. I've been interested in the harder Sudoku techniques for pretty much as long as I've been into Sudoku. So I wouldn't say I'm an expert exactly, but I do spend a lot of time thinking about this stuff. So,
well, if you're not an expert, I'm not sure who is. So I think
the people that I learned it from are the experts.
All right.
Yeah. But
so who did you learn it from? Why don't you give some of that background?
Yeah. So when I started getting into Sudoku, I was aware of Sudoku for a long time. I started watching Cracking the Cryptic after a recommendation. And I played around with puzzles a little bit. Andrew Stewart's Sudoku solver was mentioned on Cracking the Cryptic. I played around in that for a little while. And it didn't really stick. And then something happened last year that gave all of us a lot more free time. And so I kind of came back to it and started getting into it. So as I started playing more with Andrew's solver, I started finding puzzles that it couldn't solve. And so I was interested in some of these more exotic techniques for solving them. A few are mentioned on Andrew's site. Exosets are mentioned on there. But that led me to looking for other techniques. I ended up on a forum where a lot of the creators of some of the absolute hardest classic puzzles frequent that forum or used to. And eventually I started posting puzzles there. Tattooing Sunset was actually my first published puzzle anywhere.
Oh, wow. And it got featured twice.
Yeah. 3 times, sort of.
Three times, yeah.
Yeah. But yeah, from the very start, the first solution that was posted for Tattooing Sunset, somebody used multi-sector lock sets for that solution rather than all the swordfish. So I had no idea what multi-sector lock sets were at the time. So that got me started reading about those, and then future puzzles that I posted. The users of that forum like to solve things for the most part in one step, if possible.
They other than like basics, right?
Right, other than the basics.
So
they like to find the complicated solution, but that gives the one elimination that you need to just completely collapse the puzzle.
So like you start with like singles and like, doubles, triples, things like that.
Yeah.
Nothing really beyond pointing, maybe. but
Yeah,
nothing really
there's
beyond that.
there's no real point system for this game that they play, but
Yeah.
if there were, you would get kind of bonus points if you could do it so that it collapsed to singles only
Hmm.
and you didn't use anything else. But yeah, so they would post ever more complicated chains for that, including stuff like ALS nodes and memory chains and stuff that I still don't really even understand. And that's okay. Always learning.
Yeah, well, maybe we can learn that on this podcast someday.
Yeah, maybe. So yeah, so that's kind of where I got started with advanced techniques.
That's awesome. And so I also know that you've done a lot of research on set. Are you kind of on the forefront of that research?
I try to be. A lot of the discussion that led to set being a thing that was called set came from Tatooine Sunset and solutions to that. So since it was my puzzle, I felt kind of responsible for at least understanding what was going on. So
yeah, I think a lot of people don't understand how new set is. Like Fistamafel had his puzzle featured on Cracking the Cryptic about a year ago. It's a little over a year ago now, where the Fistamafel ring was used by Simon. And at that point, set theory wasn't a thing yet. Is that right?
Right, yeah. So I mentioned multi-sector lock sets,
Yeah.
and that was kind of the approach Simon took. Sam mentioned it to Simon, and that came from that whole discussion. Multi-sector lock sets has been around for quite a long time. I want to say 2012, but this alternate approach, starting from the Fistamafel ring, Fred Stadler did a generalization of Fistamafel's ideas to other intersections. Trevor Tao had the 9-dimensional wonky fish solution to the Tatooine Sunset,
Nice.
which was kind of related to the same thing. Sam was the one that related it to multi-sector lock sets originally, and sort of drove the add one set, subtract another set sort of approach that we all kind of use now. Tom Collier was involved in those discussions. I gave it the name set equivalence theory,
Nice.
kind of being silly, but
it's a good name. It you know, I think I think set is really nice because it's easy to explain. Like Simon has explained set how many times now in his videos,
yeah.
right? And
Anytime it comes up.
Yeah, and I think that what set exposes often would have been already a known technique, but one that's extremely complex to understand and definitely complex to explain. And so it's not something Simon would have been able to use on Cracking the Cryptic. Whereas what's really cool about set is it's such a generically understandable concept that it ends up being extremely useful. And then now people are creating puzzles using that concept, which then they're able to create these puzzles that are extremely difficult otherwise, but have this really nice, easily explained solution path. So anyway, we're getting a little bit off of what we wanted to talk about, but I wanted to at least give people a background on you and your contributions to the Sudoku community.
Yeah. And one of the really important things about set, and this does relate to the alternating inference chains, was us starting to realize that it's equivalent to other techniques that were already known, just a different way of looking at them. And that happens a lot in Sudoku. There are often multiple ways of looking at exactly the same logic, exactly the same elimination, but some ways will appeal to particular people more than others. So
yeah, and I think we see that a lot when you compare like Simon, how he solves a puzzle, and Mark how he solves a puzzle. Whereas Simon will be like, this is a bent triple, and so no matter what state this one cell is, it eliminates this thing. Whereas Mark will tend to look at the eliminated cell and go, oh, if this is a 5, it causes a contradiction over here. And it's the exact same pattern, but Mark will look at it from one angle and Simon will look at it from another angle. And I think that's
Right.
cool that we get those two different perspectives on the channel.
Yep.
And so, yeah, that's definitely a good observation you have there. Okay, so do we want to get started on talking about links?
Sure. Let's do it.
So why don't you just start? I know I explained it, and you said I did a pretty good job explaining it. But why don't you talk about exactly what links are and how you would describe the different kinds of links?
Sure. And kind of where I wanted to start is this is a new terminology to a lot of people. If you're not familiar with alternating inference chains, you've probably seen them mentioned on some Sudoku video, and there's this big complicated diagram with lines everywhere, and you have no idea what's going on. The links that are used in alternating inference chains, you're already using. You're just not calling them strong links or weak links. So just as a really simple example, in this puzzle, I have a 1 in this cell. What does that mean? That means I can't have a 1 in any of these cells. The reason I can't have a 1 in any of those cells is those cells see the cell that have the 1 has the 1. That's a weak link. That's all a weak link is. And that's the easiest thing that you use in a puzzle.
It's the basic rules of Sudoku, especially in Classic, where you aren't introducing all these variants that do cause some strange weak links. In Classic, a weak link is really just enforcing the rules of Sudoku. If I put a 1 in row 4, column 4, I guess row 3, column 4 in this case, I can't have a 1 in row 3, column 3. And so we describe that as a weak link so that we have some way of describing that relationship, especially in comparison to other kinds of relationships. Is that right?
Right.
Okay.
Yep. So strong links, same thing. You've used strong links before. I don't really have a good example in this puzzle for the basics that I was going to demonstrate, but you will see a lot of times Snyder notation where you have limited one candidate to 2 cells in a box. That's a strong link. What you're saying is 1 is in this cell or 1 is in this other cell. And if it's in one of those cells, it can't be in the cells that those 2 cells see. Because there's a weak link between these cells and both of these ones. So again, everything you're doing in a puzzle is strong and weak links, ultimately. Or more complicated generalizations of those.
Yeah.
But I just kind of wanted to point that out to start with.
Yeah, I think that's really good, because if we just started throwing terminology and logic at people without giving that context, I think that we would lose their attention. They'd be like, oh, I just don't understand this. I won't ever understand this. But I think what Philip's saying, what you're saying is exactly right, which is these are concepts that everyone is already using when solving puzzles. They just aren't naming them. And I think that's really important for all of the things we're going to be talking about in this podcast and anything in the future. When I make my own Sudoku videos or do my streams, I may be using a term like Y-wing, and you may not have heard that term before, but that doesn't, what's important isn't what it's called. What's important is the logic behind it. And it's not usually not that hard to understand, at least in the specific instance that we're showing, why that logic is true. And I think that that's really important when we talk about strong and weak links as well. And so do we want to go over, I don't know what your plan is in terms of order of attacking things, but we could also go over the more rigorous definition of strong and weak link as well, now that there's the context.
Yeah, we could briefly go over that. So a strong link is for 2 candidates in the grid. So in this example, I happen to have a strong link right here. In column 1 can only go in those 2 cells. This cell sees a 1 here. This cell sees a 1 here, and this cell sees a 1 here. We have to put a 1 somewhere in column 1, and there are only 2 places for that 1. So we would say there's a strong link between 1 in row 1, column 1, and the 1 in row 9, column 1. Strong links are OR links. It's not an exclusive OR. Now, in this case, we can't put 2 1s, because that would break the rules of Sudoku. But in general, you can have a strong link and both be true. All that matters is at least one is true. So that's what a strong link is. A weak link is a case where they can't both be true. So that's just what we were talking about here. There is also a weak link between these 2 candidates. And we usually talk about that in terms of they see each other. They're in the same row, they're in the same column, they're in the same box. Or if they're different candidates, they're in the same cell. So if we had, say, 3, 4 in that cell, the 3 in row 3, column 6, and the 4 in row 3, column 6 have a weak link. And that's there regardless of any other candidates that are in the cell. All of the candidates in a given cell, there's a weak link between them. Because you can only have 1 digit in a cell.
Hopefully everyone understands that. There's no Schrodinger cells, right?
Right. All of the cells in a row have weak links on the same candidate. So I can put a 1 here, or I could put a 1 here, but I can't put a 1 in both. So I can only have 1, or 1 of any other digit in each row, column, and box. Those are just the rules of Sudoku. So at the start of any Sudoku puzzles, you have a lot of weak links. And you're trying to turn those into either singles or pairs or strong links that you can use in some sort of more complicated pattern.
Awesome. And just to go back to when you had just the 3, 4 in the cell, we should point out that if it is really just a 3 or 4 in a cell, there is now a strong link between that 3 and 4, because one of them must be true. So yeah, here you're filling out.
Oh, that's a terrible example.
We don't have to be too rigorous here, but
it's got to be right.
Sure. Okay.
It'll bother me if it's not right.
So yeah, so now row 3, column 6.
So this cell sees 1, 2 in the box, 5 in the row, 6, 7, 8, 9 in the box.
Right. So
this may be a broken puzzle at this point. That's not the point.
Yeah, it can only be 3 or 4, right?
It can only be 3 or 4. So now there's a strong link between 3 and 4 in this cell. And this is what we call a bi-value cell. There are 2 possible values for that cell. So bi-value cells are one type of strong link.
And that's why they show up so much in these techniques, is because they're a strong link, and strong links are important for these techniques.
Right. And bi-value cells are often the easiest to use, because once you've pencil marked the 3, 4 in that cell, you see it. It's there staring you in the face. So you can start to see how it connects to other bi-value cells or other information in the grid. The other type of strong link is a bilocal link. So that's where you have the same digit that can only go in 2 cells. So it's the opposite of bi-value. Bi-value is one cell that can only have 2 candidates. Bilocal is one candidate that can only go in 2 cells.
And I think
column or box.
I think it's common to use the term house to represent a row, column, or box, basically a set of 9 cells that must have 1 through 9 once. So we can, I think we can, if we introduce that term, we can continue to use it.
I will probably use it inadvertently. So
yeah, so I think it's good to bring that up ahead of time. So in this case, if a value is limited to only 2 cells within a house, then there is now a strong link between that value.
And you can call that a bilocal link. Now, logically, there is no difference between a bilocal and a bivalue link. You can use them both in the same way. the distinction for me when I'm looking at these things is by value strong links are where you switch candidates in your pattern. By local, you're always staying on the same candidate, same digit.
And I think another important thing, just in terms of the human doing the solving, is because of our limited ways that we can mark up the grid and remember things, we often can know about by value cells and remember them more than by local.
Right. And I mentioned Snyder notation. Obviously, that's not the only way to notate. But for those that aren't familiar, that's where you mark if within a box, a digit can only go in two places. You would mark in the corners. They don't even have to be aligned. So you could have something like that. You would mark that in the corners. In the center, you mark these are the only digits that can go in this cell. And usually initially you're only marking cells that can only have two digits. So you're marking the by value strong links. And you're marking some of the by local strong links, but only if they're in the same box.
Yeah. And often what you'll
typically,
see... Yeah, sorry, go ahead.
You don't typically mark this in a row. Mm-hmm. Because that can get confusing. If you see this 1 here, you might think it's the only place in the box that a 1 can go, so you're going to enter a 1 in that cell. Yeah. So that's the main thing, is the buy local links are a little harder to keep track of because there's not a great way to notate them.
You'll sometimes see Simon color cells to try to remind himself, and right. I feel like there's a limited usefulness to that. I myself haven't found a good method of remembering bilocals within rows and columns. And I think that coming up with a way to do that might be sort of the next step in getting these classic Sudokus more easily solved, if I'm going to be honest. So I think that we shouldn't shy away from bilocals within rows and columns when demonstrating stuff, but I think there is an understanding that when any kind of chain involves that, it's just going to be harder for a human to spot. So
right, and colors is the way I would do it. Right now I'm going to use colors in a little bit talking about them, but
so let's move forward then. I think
let's move forward.
Yeah.
So this example, I've left out a digit. I've left out a 6, and I've done that on purpose. I'm going to put a 6 right here temporarily. So if I look at this, obviously something's going on with the 1s. And we already know there's only 2 places for 1 in column 1. Well, this 6 here now, there's also only 2 places for 1 in column 9. And these cells are aligned. If you've been watching Sudoku videos at all, you will recognize this as an X-wing pattern. We have 2 columns that are limited to 2 cells on the digit 1, and they are in the same 2 rows. So what happens if this is a 1? Well, this can't be a 1, and this can't be a 1. And that only leaves that cell to be a 1 in column 9. The other option is that this is a 1, which rules it out of these 2 cells and puts a 1 here. So those are the only 2 options for 1 in this grid. X-wings are secretly using strong links, and that's why they work. So what's happening with an X-wing is we have a strong link in column 1 and a strong link in column 9, but because they're aligned in the rows, we have a weak link between the 1 in row 1 column 1 and the 1 in row 1 column 9, and we have a weak link in row 9 as well. So this is another example of a continuous nice loop. So what we discussed, what David mentioned in the previous video on alternating inference chains, when you have a loop like this, the effect is there is now a strong link between these two cells, and there's now a strong link between these two cells. So you can eliminate one from the other cells in the row. And that's all the X-wing is doing.
So can I ask some questions here, just to, because I know people watching are probably going to have these questions too. So I guess the first question is, especially for people who didn't watch my video, but I also think I didn't do a great job explaining it in my video, is, first of all, what defines a continuous nice loop, and why does it turn the weak links into strong links?
Okay, so let's start just with the alternating inference chain.
Okay.
So the important thing with an alternating inference chain is that you alternate. It's in the name. You alternate between strong and weak links. And the reason for that, in column 1, there are two options. I could have a 1 in row 1, column 1. That's an option. If I don't have a 1 in row 1, column 1, we know there's a strong link in column 1. So if it's not here, then it has to be here. If it's here, then it can't be here.
And that's a weak link.
Because that's a weak link. And if it's not here, it has to be here. That's a strong link. So the result is either there was a 1 in row 1, column 1, or due to this alternating inference chain around the grid, we get a 1 in row 1, column 9. The result is we now know there's a 1 in one of these two cells, so we've got a strong link.
Right, and then you mentioned it before, but I just want to repeat it for people. I know we're info dumping here. Once you've formed that strong link, any cell that is seen or has a weak link to that strong link, I'm phrasing this very poorly, no longer can be that value. So it's exactly what you said, but I'm trying to say it in a more complex way that's less understandable.
Yeah, and another way you can look at it is if I tried to put a 1 here, it would rule 1 out of here, and it would rule 1 out of here. So I would need 1 in both of these cells. And that's never going to work. And
that's sort of the Mark Goodliff way of looking at the logic, right? Where he likes to approach it from that angle. Whereas Simon would use the logic of there's two possible states to the solved puzzle. One is there's a 1 in row 1, column 1. The other state is there's not a 1 in row 1, column 1. And there's a consequence to both of those states such that all of the ones in row 1, other than those two, end up not ones. Because they see a 1 in both states.
Yeah, and there's actually another way of looking at the alternating inference chain.
Okay.
It's encapsulating the same thing here, that there are weak links in row 1. But it's what's called a discontinuous nice loop. So a continuous nice loop, we have strong, weak, and it looped back to where we started. We have an even number of links. A discontinuous nice loop, say we start here. There's a weak link between these two cells. I'm going to highlight them in purple. And then there's a strong link, and then there's a weak link, and then there's a strong link, and then there's a weak link back to this cell again. So I started with a weak link, and I ended with a weak link. We already know if we alternate strong link, strong link, we get a strong link. If you alternate weak link, weak link, you get a weak link. The logic works the same way in reverse. So what we end up proving with the discontinuous nice loop of version of this is that 1 in row 1, column 3 has a weak link to itself. That's impossible. So that just eliminates the 1.
So let's think about what it would mean to have a weak link to yourself. A weak link means that
A
one
weak link
of them
means
is true, but the other's not. Or you can't
no,
have both be true, I guess is what it
they
would be.
can't both be true. Yeah,
But
so
it is itself.
I define a strong link, and I should define a weak link
Yeah.
just for completeness. So a weak link is they can't both be true.
Right. Okay. I think you did
One
say
could be
that and I
true.
forgot. So if I forgot, probably others did. So it's good we're going over it again.
Yeah, one could be true, the other could be true, or they could both be false. But for a weak link, they can't both be true.
And so if a singular candidate in a singular cell ends up with a weak link to itself,
Then it has to be
has
false.
to be false. Because if it were true, then both links would be true, and that can't. And we know
Right.
that by definition that's untrue. So
Right.
so a discontinuous nice loop starts with a weak link, comes back around, and forms a weak link to itself.
Right.
Thus eliminating itself, basically.
Right.
Now, I think that there's an underlying concept here that we haven't gone over, which I think would maybe a question in people's heads is, or maybe they're just now understanding it, is that by following an alternating inference chain, you are forming new weak and strong links as you go. Right?
Right.
So maybe we can talk about that. I can explain it, you can explain it.
Go ahead.
Yeah, so my understanding of it is I don't have control of a mouse, but my understanding of it is basically let's take the continuous nice loop. Let's start with a strong link. If I have a strong link to a cell and then I go weak link, I'm saying I'm now have formed a weak link from where I started to that new destination. Is that correct?
Not quite.
Not quite. Okay.
So the chain has to start and end with the same type of link.
I see.
For this to be valid.
Okay, so if I go strong, weak, strong, now
right.
there's a strong link between those two
right.
items. Okay.
Now, in this example, we went strong, weak, strong, and we ended up with a strong link between two cells that see each other. So you can kind of think of that as turning a weak link into a strong link. I think you mentioned this in your previous video.
Yeah.
They don't have to see each other, though, is the thing.
Right.
So the reason I chose this particular example, let me just get rid of the highlighting. Without the 6, is that actually I want the 6 there. Because now there's still two places that one can go in column 9, but they don't see each other. So what do we do then? It's useless. They don't see each other.
Not so much.
Not so much. So when they see each other, you get things like continuous nice loops, or in this particular case, you get an X-wing. When they don't see each other, though, you can still make eliminations, and you can think about it in the discontinuous nice loop sort of way by, say, including this cell. What happens if this is a 1? Well, now these can't be 1. That's a bad
we have
color.
problems, yes.
So if those can't be 1, then these have to be 1, and we have problems because they see each other.
Yeah, so people would call this form a skyscraper, I believe.
Right.
Yeah.
Yes, this is a skyscraper. So a skyscraper, the formal definition, I guess, is a pattern with two strong links with a weak link in between, where both of the strong links are bilocal. So it's a pattern on a single digit. Additionally, both of the strong links are either in columns or in rows. They're not in boxes.
And I think the really interesting thing of how you're explicitly stating this is I think people's heads should be spinning here like, well, why does the strong link have to be bilocal? Why does it have to be on the same candidate? Why is it columns or rows and not boxes? And I think these are really important questions to ask. And so once we start looking at the logic in this more generic sense, you should be thinking, well, can I form a skyscraper but have my strong links be bi-value cells? What would that look like? Is that called something else? Or, is that useful? And so
Right.
I think that this is what's really cool about thinking about these techniques this way. But anyway, continue with your explanation of the skyscraper here.
Yeah, so in this particular example, these two cells in box 1 and these two cells in box 3 see both of the ones that have a strong link now.
And we should point out that the given 6 and the given 2 also see it. But in this case,
the given 6 and given 2 also see it,
yeah.
but they already can't be 1, so yeah. I didn't highlight
for completeness. I think
yes, for completeness.
If there weren't a given there, then that would be something that would be eliminated as well.
Right. So those 4 cells now can't be a 1. Now that's not as powerful as the X-wing. The X-wing, we had a total of 8 new cells that couldn't be the 1. It's half as powerful, but it's still useful. And
in this particular example, it eliminates the 1 from the same number of cells as before, though, actually, because we have those 3 given ones there.
Well, yeah, so it eliminates in the same number of cells at the top of the grid.
Yeah.
The X-wing also eliminates at the bottom.
Right. Oh, yes, of course.
Yeah.
I forgot about that.
Yeah. Yeah, loops tend to be a lot more powerful in terms of eliminations. And there's a reason for that, and we can go over that. I'll bring up the X-wing example again in a minute, why that is the case. But so skyscrapers, you make eliminations on the cells that can see both ends of the chain. And that's pretty much how all alternating inference chains work. You're looking for candidates that see both of the candidates that have the new strong link.
So if I can try to describe this in a more robust way, we have starting at row 1, column 1, on the top left, we have a strong link to row 9, column 1. If you can point at the cells while I say them, that's probably helpful.
Sure.
Yeah, so row 1 has a strong link there, which then has a weak link to row 9, column 9, which then has a strong link to row 2, column 9. And so now that we've started and ended with a strong link, we can now say there's a strong link between row 1, column 1 and row 2, column 9, which is new information that we didn't know before. And now that we can form that strong link, any cells that see both of those cells, i.e. any cells with a weak link to both of those cells, cannot have that candidate in it anymore, can't have a 1 in it.
Yeah.
And so the result's the same. But
those strong links that we get from chains, skyscraper in this case, but whatever the pattern is, we keep them. They don't go away. We've proven that one of those two things has to be true. Now, eventually, we're going to determine that this cell is a 1. And so now our strong link isn't useful anymore. We know one of them is true, and we already have that one of them is true.
And what you pointed out is they could both be true, so it doesn't even eliminate a 1 from row 2, column
1. Right. But until we reach that point, there can be cases where you get a strong link, you make some eliminations, and then later on, you come back to it. Say you're able to put a 1 here. That eliminates 1 from this cell, and by our strong link, puts 1 there. Now, we could have gone through the weak link to do that, but there are cases where you can use a pattern and then later use the pattern for something else.
And it just feels good to do that, use information that build off of things you've learned. And probably, I was going to say it's actually probably harder. If you thought remembering strong links in rows and columns was hard, try remembering strong links that you've discovered through AIC. But if it ended up useful, maybe you will still have it highlighted, and maybe you'll remember that.
Right.
Right.
Yeah, and that's why often you find an X-wing, you highlight those cells. And even if it doesn't end up being useful, at some point you're going to place that digit, and you're going to feel really good about knowing where the other
just immediately plonk it in the other
cell
side,
is. Yeah.
I have confidence in my ability to understand the X-wing.
Right. Yeah, so the skyscraper is one pattern of a general type of pattern called a turbot fish.
This
Why
is
it's
something
called
I
that,
haven't gone over.
I have no idea.
It's a kind of fish. It's like a bottom feeder, if I remember
It is
right.
kind of fish,
Yeah.
but I don't know why
It's like
that name was settled on for this type of pattern.
I feel like that's true of most Sudoku patterns, like
Right.
swordfish and jellyfish. Even like why? Who knows? It's a fish,
Right. So yeah, turbot fish are basically single-digit patterns. You can see these things called X chains or X loops if they loop on themselves occasionally. But that's what they're called. So if you ever see the term turbot fish, that's what it is. So I mentioned a skyscraper specifically is either strong links in columns or strong links in rows.
Mm-hmm.
So if you're asking the question, well, why does it have to be that way? Why can't it use boxes? It's because there's another pattern that is named something different that uses those type of links. Having a more general understanding of how these things work is a lot more useful, really, than memorizing 15 different names for things. Yeah. Because they're all related. But another common one that you'll see, I don't have an example of it up, is a two-string kite. One of the recent videos, the tattooing pod racing one, you mentioned two-string kites. A two-string kite has a strong link in a row and a strong link in a column. And the weak link is in the box. So that's just another type of the same thing.
Is that the same pattern as the skyscraper?
It's the same pattern other than the row column
it's
box.
It's the same AIC concept.
It's still a two strong link pattern.
And now see, you can have to my brain, the skyscraper and the two-string kite are completely different things. But when we start
different.
And they look different, and you find them, you still find them by highlighting all of a single candidate and looking.
Right.
It's really cool that the result, if you look at it from a logical perspective, when we talk about these links, it's exactly the same. And I could even see a situation where you maybe form a strong link with a skyscraper and then use that strong link as part of a skyscraper-esque other thing happening, right? And so now you can recognize that. It would be kind of cool to try to construct a puzzle like that. But
sure, and there's no particular limit on how many strong links you have.
Yeah.
For turbot fish, you can have skyscrapers that have 3 strong links, and you just call them a 3 strong link skyscraper. You can have kites with 3 strong links, and you call them a 3-string kite rather than a 2-string kite.
All right.
That one I understand where the name came from. But yeah, so these are all single-digit patterns. So whenever you have a single-digit pattern, all the strong links are going to be bilocal.
Right.
You can also have patterns that use multiple digits. The Y-wing or XY-wing or bent triple, whatever you want to call it.
3 names for the same thing, by the way.
3 names for the same thing. Is a pattern of 3 bi-value cells, where one of the cells is the pivot.
Do you want to just like randomly put one on the board, even though it's not correct? I know you hate that.
Yeah, I can stick something in here. Let's see.
So these are not coming from the board. We're just using it as a canvas here. But
let's do this and this.
It's the tiniest possible Y-wing.
Tiniest Y-wing. So these don't even have to be in the same box for it to be a Y-wing. That's not the important thing. So in this example, we have 3 bi-value cells, and they're on 3 total digits. Each one of them is different. So 3, 4, 3, 5, 4, 5. One of the bi-value cells sees both of the other 2.
So we would, with our terminology, we would say it has a weak link to the other 2.
Right. So all bi-value cells have strong links between those 2 candidates within the cell. And then the pivot sees both of the other cells, there are weak links between, in this case, there's a weak link between the 4 in row 3, column 6, and the 4 in row 4, column 6. In this case, there's a weak link between the 5s in row 4, column 5, and column 6. So again, we have an alternating chain. We have a strong link. If we start with the 3, we have a strong link between the 3 and the 4 in this cell, a weak link to the 4 in this cell, a strong link between the 4 and the 5 in this cell, a weak link to the 5 in this cell, and a strong link between the 5 and the 3 in this cell. Since we alternated strong, weak, strong, weak, strong, that is hard to say. The result is we have a strong link between the ends. And it's important to note the ends are not these two cells. The ends are the candidate 3 in this cell and the candidate 3 in this cell.
Yeah, links are always between candidates, never between cells, right?
But the result is there's a strong link between 3 in these cells, and so I can eliminate 3 from any cell that sees both of them.
And because there's a shared box in this case, there's a lot more eliminations than a typical Y-wing. But
right. Now, why can't they see each other, these two?
Why can't they see each other?
Yep.
They don't share a row, column, or box.
In a Y-wing, though. Why is it not a Y-wing if they see each other?
Okay. Because it's a triple.
Because it's a triple.
Yeah, it just has a different name.
So, surprise, naked triples are actually continuous nice loops. You just never call them that.
Right.
And you shouldn't call them that. When you're looking at this, you don't need to think,
continuous nice loop.
Oh, there's a strong link here, and a strong link here, and a strong link here, and a weak link. You don't need to think that. You just think they're 3 digits, 3 cells, so I can eliminate those digits. But when you don't have a nice naked triple, and instead it's over here, then you're starting to look for AICs. In this case, you're looking for a Y-wing. The terminology for wings are 3 strong link patterns, which are AICs, but they're not on a single digit. They're never on a single digit. And the naming for them depends on what type of strong link you have.
Interesting. Okay.
Yeah, so the Y-wing is the most common one that people know about. It's also the simplest to see because they're all bi-value cells.
Yeah, typically when you're going through a solve, once you convince yourself there are no single value options to go with, you start looking at all the bi-value cells and seeing how they connect to each other, and that's when you spawn the Y-wings.
Now, just as a quick example, let me get rid of some of this highlighting. Let's see. Let's say that I couldn't have one in these cells at the bottom. We already know we had a skyscraper in the purple cells.
Yep.
If instead, this isn't actually going to work in the grid, but that's okay. We're just pretending.
Yep.
If I had bi-value cells at the ends. So now I have a bi-value cell, strong link between 5 and 1 in this cell. I have a weak link. I had a strong link before, but it's also a weak link between the ones in row 1, column 1, and row 9, column 1.
And I think this is something important to point out, is just because you formed a strong link doesn't mean you're not allowed to use it as a weak link if you need to. So, because we have to alternate. That's an important part.
Right. I have just defined this as being a strong link.
Yep.
We're
magicking it into being a strong link.
We're magicking it. I've ruled out 1 in the gray cells here. So I'm saying 1 has to go in one of these 2 cells. Mm-hmm. There's a weak link between 1 in column 9 in rows 2 and row 9. And then there's another bi-value cell, so a strong link between 1 and 5 in this cell. So this is a W wing. it looks like a skyscraper, but the links are inverted. So on 1, it's weak, strong, weak. And what makes it a wing is the additional strong links are by value to another digit. So the result is I have a strong link between the 5 and these cells. So I can eliminate 5 from those red cells, the same red cells as the skyscraper. So that's just another example of a wing. There are probably 8 or 9 different named wings.
But they all use the
same
basic concept.
They all use the same basic strong, weak, strong pattern.
And then the strongs at the end end up forming a new strong link, which does eliminations of some kind.
As far as solving goes, you don't need to know what they're called. The important thing is understanding the logic.
And you don't even have to call it strong, weak, strong necessarily, right? Because you could think in your head, so sorry, you're going to have to point for me again, but starting with row 1, column 1, you could think, okay, that's 1 or 5. So if it's a 5, I eliminate 5s from the red cells. Well, right. What if it's not a 5? If it's not a 5, well, it has to be a 1. That's the only other option. Well, now that it's 1, now in row 9, I can't have a 1 in row 9, column 1. I have to have a 9 in row 9, column 9, which now eliminates the 1 and puts a 5 there. And I haven't thought about it as strong or weak links, but guess what? I've just followed an alternating inference chain, and I've proven that there's a 5 either in row 1, column 1, or in row 2, column 9, or both. But either way, the red cells, which are seen by both of those cells, have a 5 eliminated from them. And I think when a lot of people use W wings, they aren't thinking of it starting with one of the, like they aren't starting with row 1, column 1. They're starting with the strong link in row 9.
Right.
And they're seeing 2 by-value cells that are the same 2 candidates that are seen by both ends of the strong link, say, in row 9. So if you undo to undo what you've filled there, I would spot a W wing by seeing first the strong link on row 9 on 1s, and then seeing that they both see a 1-5 candidate cell, and so therefore one of them must be a 5, because if both of those were 1s, I would have nowhere to put a 1 in row 9. Right.
And again, different people will see things differently. Another way you might see this is, oh, I have 1-5 limited in these 2 cells. Is there any way I can connect them? And that's how you spot that strong link. So whichever way works, or just trying things out in your head and see if it makes sense.
Okay. So I think this is probably one of your other tabs that we haven't gotten to yet. So maybe this is the time to transition to that. But I think that this really cleanly transitions to the idea that, well, why does a wing have to be 3 strong links? Can't we form more strong links and then use those? So can we extend, say take the Y wing, the simplest example. Can we extend one of the, like from the pivot, go through a few cells first, and still have the same logic of the Y wing?
Yeah, so
I don't know if that's one of your examples or not, but
it's a little different.
Okay.
But it's going to generalize chains. So I designed this. I was trying to make a puzzle that demonstrated a particular technique, and this one didn't quite work. So it has the technique, but it doesn't solve the puzzle on its own. And I mean, that's just a total failure, right? No.
You have to do more techniques to solve it.
Sometimes those are still good puzzles.
Yeah.
But I thought it would be a good illustration of a technique. So there's a lot going on here. There are a lot of things that you could look at to start with. There are probably some singles somewhere. I don't know if you see any singles.
I haven't actually looked. Let me stare.
So I can limit 2 in these 2 cells. Can limit
7 in box 7.
7 in box 7. I can go in those 2 cells.
And 9's in box 7 as well.
9's in box 7. 9 in box 3.
Oh, center mark. Oh.
Yeah, I'm center marking. What is happening?
How could you?
I don't even know how I did that. All right.
There's a lot of 7s on the grid, actually. You can limit 7 in box 9, but it's not that useful of a formation. Again.
Why does that keep switching over?
I don't know. You're hitting some button that does it.
Oh, yeah. It's because I'm selecting multiple cells. Anyway.
4s in box 3.
4s in box 3. Yep.
I'm sure there's more, but go ahead and say what you want to say.
All right. So there may even be some digits that you can get doing this. I don't remember off the top of my head. But let's start looking at cells that are limited.
Okay, so we're back, and Philip missed a 6 as a given in this puzzle, and also we decided just to fill the important cell candidate. So if you examine those, you'll see that just they see those numbers. There's nothing special going on. So we'll save you the time of watching those get filled. But now Philip's going to explain. Can you explain what we're doing with these cells?
Right. So most of these are bi-value cells. If all of them were bi-value cells, we would have a pretty good idea what to do with them, right? So if, let's say this were not, if it weren't possible for this to be a 5, I think that should work. We would have a strong link on 1 and 3 here. A weak link on the 3s.
Yep.
A strong link 3 to 5. A weak link on the 5s. Strong link on the 2s. A weak link. A weak link on the 2s. I skipped a thing. Strong link between 5 and 2. Weak link on the 2s. Strong link between 2 and 5. Weak link to this 5. Strong link between 5 and 6. Weak link between 6s. Strong link between 6 and 1. And weak link between 1s.
And we started with the strong link between 1 and 3, right?
Right. So strong, weak, etc.
So this is a continuous nice loop, if I remember
right. This would be a continuous nice loop if that 5 weren't there.
And that forms a strong link between all of the weak links we mentioned. So we get a ton of eliminations.
And it forms a weak link between all of the strong links.
Interesting. Okay.
In this case, it doesn't matter because they're bi-value cells.
So what would that mean? That means that
it doesn't add anything in this case.
Oh, okay.
But it could. In some cases.
Gotcha.
Yeah. So you can have situations with a continuous nice loop where you know only one of your strong link candidates can be true.
So I guess one way to think about that would be if I were to fill a 3 into your highlighted cell, I can follow that around the loop and get 5, 2. And so we basically have formed, which of course eliminates 2 from row 7 column.
Started with 3, so 5,
3, 5, 2. That eliminates
5,
2 from there.
6.
You can stop there. You don't have to go all the way around. But what I wanted to point out is that you can think of that as now there's a weak link between the 3 in row 3 column 3 and the 2 in row 7 column 7.
That's
so
right.
if we put a 3 into row 3 column 3, we can eliminate a 2 from row 7 column 7. And of course you would not do that. You would go through the chain that we just did, but
right.
That's the way to think about those weak links that have been formed.
And it's important to note it works the other way as well. If you put a 2 here, you get a 5 here and a 3 here, and now you can't have a 3 there.
Yeah, and so that's why it's a weak link, because it works both ways.
Right. Yeah. So this would be what we would call an XY ring.
Mm-hmm.
So this is very similar to puzzles that David has done on the channel, just bigger. This one has 6 cells instead of 4.
Yep.
You can do this with a lot of cells. I have a puzzle with 8.
Nice.
But yeah, this wouldn't be a very interesting example if it was the same thing as you've already seen before. So what does this 5 do?
It's a good question. Is it
It
like
messes
a
everything
yeah?
up.
It
That's what
almost
it
feels
does.
like the what was it called? The jellyfish that wasn't quite a jellyfish that you had.
The finned
The finned. So is
jellyfish.
this like a
Yes.
finned wing?
It's not really a fin, no.
Okay.
So there are a couple different ways of looking at this. One is you can look at it as strong links on groups. So, or weak links on groups. Let's say we look at this cell. This could be a 2 or a 5.
Yep.
Which one do you want to start with?
Let's start with 2.
If I put a 2 here, I have to put a 5 here.
Mm-hmm.
I have to put a 6 here. I have to put a 1 here. And now I have a 3-5 pair.
Right. And so that does eliminate 3s and 5s from the rest of the row.
Still eliminates 3s and 5s from the row. It's not quite as powerful as before. We only got 4 digits filled in, but we got a pair. It's almost as powerful. If we put a 5 here... Oh.
Well, one thing I can note right away is we're already eliminating 5s from the row in that case as well.
We're eliminating 5, yeah. So 3, 1. We've got a 3-5 pair here now, right?
Yeah.
So that's a little suspicious.
Mm-hmm.
So one way we can think about this is there is a strong link between having a 2 in this cell and having a 3-5 in these 2 cells.
Okay, because one of the 2 must be true.
So either there's a 2 here,
mm-hmm.
or there's a 3-5 in these cells.
Got it.
Okay. There is a weak link between having a 3-5 in these 2 cells and having a 3-5 in these 2 cells.
Which I think is understandable. You can't have
you
both.
Can't have 3-5 in 3 cells.
Exactly.
Okay. And then there's a strong link between having a 1 in this cell and having a 3-5 in these 2 cells.
Okay, so we're kind of forming a loop, but we're using the 3-5 pair as one of the nodes.
Exactly. So that's one way you can look at it, as sort of a grouped alternating inference chain, or a grouped.
So does this still form a continuous nice loop if we include those?
Does still form the continuous nice loop. What it tells us is either there's a 3-5 pair here, or there's a 3-5 pair here. But either way, there's no 3s and 5s in those cells.
Does it still also form, say, a strong link between the 5s in row 7?
5s in row 7, yeah. So everything else works identically.
Yeah, so we don't just eliminate in row 3. We don't just get that 3-5 pair. We also eliminate 5s from the rest of row 7, and 6s from the rest of row 7, and 1s from column 3. It's super powerful still. Yeah,
with the loop, any weak link that we had before is now a strong link. And I should kind of go over why that is.
Yeah, I think that's important.
Let me go back to this example, because it'll be a little clearer. Oh. And that. I'm going to put my 6 back here.
Okay. So we're back to the X-Wing.
So we're back to our X-Wing. So with an alternate inference chain, say this was one of the strong links and this was the other strong link. If I were just looking at it as strong, weak, strong, I can start with row 1, column 1. This is a strong link to row 1, column 9.
Row 9, column 1.
A weak link to row 9, column 9. Did I say it backwards?
You said it backwards.
I probably did.
You, yeah.
I knew I was going to at some point.
Who doesn't? Hey, people in chat will say row 4, column 6, and I'll highlight like row 5, column 3, and go, "What do you mean this cell doesn't do anything?" It's like, what did I read and what did I select?
Right. So a weak link between row 9, column 1, and row 9, column 9, and then a strong link between row 9, column 9, and row 1, column 9.
Okay, yeah.
I was
now we're thinking
determined not to say that backwards. So we went strong, weak, strong, and we ended up with a strong link between these two cells.
Yeah.
Because it's a loop, because these are weak, we can go the other direction. So this time I'm going to start down here. I'm going to say this is a strong link from row 9 column 1 to row 1 column 1. There's a weak link between these two cells in row 1, and there's a strong link between these cells. So the point of the loop is I can reverse it. If there wasn't a weak link here, I couldn't reverse it.
Yeah, so the skyscraper, it doesn't reverse, which is why you don't get eliminations in the same places as the X-Wing.
Right. But in this case, I have a weak link here, and I have a weak link here. So I can go in either direction.
Right.
Now, to be clear, any alternating inference chain works both ways in the sense that I can start at either end. So I could have started row 1, column 9 and gone this way.
Okay.
But that would just give the same strong link.
Okay.
The benefit of the continuous nice loop is I can start in a different cell.
So you can start in the middle.
Right.
If we were to draw, like, write out this chain, like I was doing a notepad in my previous video,
yeah,
I could start in somewhere in the middle of what I wrote, and I could take what was to the left of it and just transplant it to the right, and it would still work because it's a circle. Okay, so we've brought up a notepad here so we can actually write this out.
All right, so this was our chain. We have the 1 in row 1, column 1.
Yep.
Has a strong link with the 1 in row 9, column 1.
In case you didn't watch my video before, this is not an equal sign. This is literally just two lines. Like, you think of it as two lines because it's a stronger link than the weak link, which is one line, which we use a minus sign for.
Yeah. This is called Eureka notation. Okay. I don't know why it's called Eureka notation. I don't know who named it.
That's what it's called. Mr. Eureka named it.
Somebody out there can probably tell me. But
I wouldn't be surprised if there's some guy out there with the handle Eureka and it's his notation.
Right. That seems to be how a lot of
just like Snyder notation. That's Thomas Snyder's last name.
It's
his
Thomas
notation.
Snyder. Exocet, I think, is from a username. Maybe not.
Sudokult, which is a great name.
That one definitely is a username.
Yeah, it's a username. Yeah. In fact, he wanted to name it something else, and everyone just called it by his name anyway.
Nah, that's a Sue. All right, so and we have a weak link between row 9, column 1 and row 9, column 9, and a strong link to row 1, column 9.
Yep.
Make that just
and then that has bigger. Well, that goes off of my capture, so okay.
Sorry.
You can just go to the next line.
All right.
This is visible. Okay, yeah, that's good. All right.
It's going to be jumping all over the screen now.
That's fine.
All right, so this
should we mention that there's now a weak link to the 1 in row 1, column 1 as well?
Yeah, I'm going to get to that.
Okay.
So this is our chain without the row 1 weak link.
I see. Okay.
So what that would result in is a strong link between the endpoints, row 1, column 1 and row 1, column 9.
Nice.
However, we have a weak link as well.
Yes.
Those are both in row 1. They see each other. So this is now a continuous nice loop. And the nice thing about continuous nice loops is you can traverse them in the opposite direction. So when I didn't have this weak link here, I had to start here or here and go strong, weak, strong.
Yeah.
Right. But now that I have this weak link here, I can start with row 9, column 1. Because this is a loop. And this, I don't know what the best way to notate this is. We'll just leave it like this.
Yeah, just start a new one. So we can start with row 1, kind of 1, and then we're moving to the left now. So we have a strong
now we're moving
1.
backwards.
Yeah.
So we got to row 1, column 1, but that was here, but it's also here.
It's the same
and
candidate,
there's a
same
weak
cell.
link.
Yeah. And so we can just keep going backwards. Probably go to the new line at that point. Yeah.
Yep. And there's still a weak link here. Back to
it's
the
still a
original
loop.
cell.
Yeah.
It's still a loop. But the point is, since we could go to the left now, we can now see there's a strong link between these two cells.
And so now we've proven both weak links that were in this loop have become strong links.
Right. Yeah, and these were originally in the middle of our chain.
And so without having formed that loop, we cannot make that determination.
Right.
But because it loops, we can start anywhere in the loop and go in any direction we want, and it'll still be a valid AIC, and then that forms those strong links.
Yeah, and it is important to mention, I think we've mentioned this at some point, but I'll just bring it up again. If I have this chain with 3 strong links,
yep,
this results in a strong link between A and F, the ends. But I can stop at any point.
Yeah, you can stop early and it's still a valid
So I could
chain.
stop right there. And now this becomes a strong link between A and D. I could also just look at this part and get a strong link between C and F. So as you're walking along these chains, you're generating strong links every time you alternate.
Yeah, more and more as you keep going.
More and more. Yeah, it grows quadratically.
Yeah, that's a good way to put it.
So, yeah, so that's important. Having this weak link, though, back to the beginning means I can now go between E and D, which isn't obvious from the way I'm writing it, but E to F to A to B to C to D.
Yeah, so we just went all the way around, and now there's a strong link between E and D.
Right. So that can be an important thing to look for, whether it loops or not.
And then the discontinuous nice loop that you mentioned, where it's a weak link on both ends?
Yeah, so a discontinuous nice loop would look like...
Doesn't it start with a weak link? Or
yeah,
I see.
Started with the wrong thing. Okay. Yeah, so this would be our regular AIC, alternating inference chain. We've got a strong link between A and D. The eliminations that we're making are on candidates that see both ends. If they see both ends, then there's a weak link. So there's a weak link between E and A, and there's a weak link between D and E. And what writing it in this form gives us is that there is a weak link between E and E.
Which makes no sense at all, which we talked about before.
Right.
E can't possibly be true.
E and E can't both be true. And since they're the same, that means they're both false.
Yeah.
So that's what a discontinuous nice loop. You can also have sort of the opposite of that, where you have an odd length loop, but it starts and ends with strong links. So the result here is a strong link between A and A. So at least one of A and A must be true.
I wonder what A is. Yeah.
Yeah, so those are the different types of loops you can have. If you start and end with a strong link, then that cell is, or that candidate in that cell is true. If you start and end with a weak link, it's false. And this, if you alternate, you have a continuous nice loop.
And this last one that you said, that's called an autogon, if I recall?
No.
That's not an autogon? So, okay. Sorry, I brought it up then.
An autogon is kind of related, but it's a little different.
Okay.
Yeah.
We don't have to explain it in this podcast. Then.
Yeah, that can be a future video. Yeah. So different types of chains and loops, and that's what it looks like in that notation. So that's the power of the continuous nice loop. You can go both directions, and all of your weak links are now also strong links. Okay, so that's one way of looking at this, is as a 3-5 pair. The other way of looking at it,
there's another way.
This is what you'll see it called if you look at it in a solver. So Sudoku would list it as this. This is what's called an almost locked set.
Mm-hmm.
So a locked set is when you have a certain number of digits and exactly the same number of cells.
On this channel, I call it a tuple, but I think locked set is the more appropriate term.
Right. So a quadruple.
Yeah.
You have 4 candidates and 4 cells. So it's a quadruple. It's a locked set. Those 4 digits have to go in those 4 cells. Nothing else can go in those 4 cells, and those 4 digits can't go anywhere else in that house.
Right.
We don't have that here. We have 4 candidates and 3 cells. So this is what's called an almost locked set.
Yeah.
It's one away from being a locked set.
So if we eliminate any one of those candidates from the cells, like eliminate the 1, for example, then we get not just a locked set, but we get a 3-5 pair and a 2 single, for example.
Right. If we were able to put a 5 here, now we would have 2, 3, 1.
Yeah.
If we were able to put a 2 here, we would have 5, 3, 1. Regardless of what the digit is. If we were able to put a 1 up here, we'd have a 3-5 pair and a 2. You can also have almost locked sets, where you have too many candidates.
Yeah.
They don't come up as often. The important thing with this almost locked set, and the reason why I wanted to mention it, is almost locked sets can give you strong links.
Okay.
The way they do that is when there's a candidate that can only go in one place, and there's a different candidate that can only go in one place.
So the 1 and the 2 in this case that you were highlighting.
Yeah. And we talked about this sort of already. If this is not a 2,
yeah,
then I have a 5 here, a 3 here, and a 1 here. So either this cell is a 2, or this cell is a 1. The reason one of those has to be true is if I take out 2 of the candidates from my almost locked set, now I have 2 candidates for 3 cells.
Yeah, we can only give up 1 of the candidates. We can't give up more than 1. So if 2 of those candidates are both limited to 1 cell each, 1 of them must be true.
Right. And it doesn't have to be just 1 cell, but it's going to be a lot more useful when it's 1 cell, or if it's a couple of cells that are in the same row and box, say.
So what it sounds like is if 1 of them has to be true, that's a strong link. That's a definition of a strong link.
That is a strong link. So we have a strong link here between the 1 in row 3, column 3, and the 2 in row 3, column 7.
And we're going to form a continuous nice loop using that. That's what I'm seeing.
We're going to use that. Now, we looked at these as bi-value cells before, but they are also an almost locked set. If you have a chain in the same house of bi-value cells that connect to each other, you're either going to end up with a tuple if it loops back on itself, or you're going to end up with an almost locked set. So again, in this case, this could be a 1. If it's not a 1, then we have a 5, 6 here. So we have to have 2 here.
Yep.
So again, there's a strong link between 1 in row 7, column 3, and the 2 in row 7, column 7. So we had a strong link up here. I'm just going to mark those. I need to settle on a
color scheme.
color of choice. And we have a strong link between those cells in row 7. And of course, we have a weak link between the 1s in column 3, and we have a weak link between the 2s in column 7.
This almost sounds like an X-wing to me.
It is very similar to an X-wing, except it's 2 different digits.
Right.
So it's most similar to a XY ring. But it's smaller even than that, really.
It also reminds me of the W wing that you described, because we have the 2 bi-value cells that are
A little bit, yeah.
Yeah.
In this case, we have the 2 bi-value cells. So we have a strong link from the 2 to the 1. We have a strong link from the 2 to the 1. And then the 1s are connecting. So yeah, I can definitely see that connection. With a W wing, it's a little more complicated over here with the 1s.
Yeah.
We have weak link, strong link, weak link. But yeah, it kind of looks like a 2 strong link W wing, if that makes sense.
Yeah.
It doesn't really make sense.
No, it doesn't. But... I'm making connections in my head that sometimes.
So what this is actually called is an ALS XZ ring.
ALS XZ ring. That's definitely rolls off the tongue.
Right. So I think I understand why it's XZ. But I'm not 100% sure on that. So
why don't you describe what it does? Too much. Let's see how this works.
But yeah, the distinction is there is also an ALS XY wing or ring and an ALS W wing. And they're all doing slightly different things. The ALS XY wing is based on a Y wing, an XY wing.
Yeah.
Just using ALSs. The ALS W wing looks like a W wing, just using ALSs. So this one, the XZ, the X and the Z are the candidates, the 2 candidates. So 1 is X and 2 is Z, for example. But what it's doing, the ALS is creating a strong link between the 1 here and the 2 here. And between the 1 here and the 2 here, we have a weak link in the columns. Okay. So we have a loop.
Yeah.
The result is this was a weak link. Now it's a strong link. So these cells can't contain 1. Most of them already couldn't contain 1, but they really can now.
They really can now.
These cells
can't have 2.
Can't have 2.
Most of them couldn't anyway, but now they really
Most of them couldn't anyway.
So it actually has the same effect as the X-wing. It's just 2 different values on each side.
But wait, there's more.
There's more. Uh-oh.
These cells can't have 3 or 5 in them.
Because we've taken... Because 1 of 1 or 2 must be true. No, I don't understand it. Sorry. Maybe you can explain it.
Okay, so if we go back to the other way that we were looking at it, we have a 3-5 pair here, or we have a 3-5 pair here.
Right. So the last time we looked at it, it did do those eliminations. I remember that.
Right. The reason it works in this formulation with the ALSs, or the reason it works because it works. But the way you can think about it, if one of these was a 3 or 5, say this was a 5, the only way that can happen is if I have a 2 and a 1 in that ALS.
Right.
Which is fine for this row. But
it's not
it
fine
eliminates
for the
1
other
and
ALS.
2 in the other ALS. So what the ALS is doing, it's hiding a weak link, a grouped weak link on the other candidates.
So it's sort of a smoother way to think of what you described earlier.
Right. So we get those eliminations in this row, and of course we get the same eliminations, this time on 5 and 6.
So
and
can we
row
say that
7.
not only is there now a strong link between the 1 and the 2, because, well, the ALS itself had a strong link between the 1 and the 2, but now
Right.
we've also formed a weak link between the 1 and the 2, which is
We have
important.
also formed a weak link between the 1 and the 2. And yeah, that's what we were talking about earlier.
Yeah.
It also turns strong links into weak links when you have a loop. And that's where it's useful here.
Yeah, I could not possibly think how that could be useful, and now we're seeing it
Yeah.
in action where, because there's
Yeah,
a weak
and-
link, they can't both be true, which means one of them is the one that's not part of the almost lock
Right.
set. So the ones not involved in that must be in the lock set, the almost lock
Right.
set.
And it looks a lot like an X-Wing. If there's a 1 here, we immediately know there's a 2 there. Oop.
Yeah, that's crazy.
And if there's a 1 here, we immediately know there's a 2 there.
So now there's a strong link between, or there's a weak link between those diagonal cells as well. Then, if you can think about it, right?
It's not a weak link. It's not a strong link.
Oh,
They are connected.
they're connected. What?
They
Not
they
as
have
well.
the same truth value in some sense.
I see. Okay,
So either there's a 1 here and a 2 here, or there's neither of those.
I see.
Yeah. I don't know that has a name in link terminology. Anyway, there are other ways of getting at it other than the ALS. We talked about one of them. But that's the net result. When you're looking at it with the ALS, we had a strong link due to the ALS. Because we have a loop, all the strong links became weak links.
And I think
While at the same time, all the weak links became strong links.
To me, it really feels like if you want to get good at solving, and especially fast at solving these complex classics, the ALS is the sort of cornerstone to that, in my opinion. Like being able to locate ALSs and thinking about the consequences of those, because it seems like there's a lot of different techniques that are uncovered by having ALSs.
Yeah. Now, the danger with ALSs, if you're solving puzzles and you're thinking, oh, I learned this new ALS thing, I'm going to apply it everywhere. Be careful.
Who would do
because
that?
there are ALSs everywhere.
Yes.
You will find them all the time. Just as an example, there's an ALS in these. No, let me get all the cells. There's an ALS in these 4 purple cells. I haven't even written what the candidates are.
It's just
I don't
guaranteed.
care what the candidates are.
Yeah.
But I know there are 5 candidates left in this row. I highlighted 4 cells in the row, so there's an ALS. Is it a useful ALS? Probably not. But it might be. I think I'm probably close to one that is useful. So I happen to know a one-step solution to this puzzle. Is an ALS XY wing, and one of the ALSs is in this row. I don't remember specifically where it is.
Yeah, that is definitely a danger. There's ALSs everywhere. Once you understand the ALS, you just say, oh, here and here and here and here. But then what do you do with them? Often nothing.
Yeah. But usually the useful ones are the ones where 2 of the digits are limited to one place.
And being able
in
to
the
think
ALS.
of forming that strong link may unlock secrets of the puzzle that you wouldn't have otherwise understood.
Right. And I chose the ALS XZ because it's the simplest.
Mm-hmm.
Just like how you can have an X-wing or you can have a skyscraper where 2 of the ends don't line up. It happened that these lined up and that these lined up. Everything lined up nicely. It doesn't have to work that way. This 2-5 could have been in this cell instead. I would still have an ALS XZ, but it would look more like a W-wing or a skyscraper.
Right.
I would have strong link, weak link, strong link, showing that there's a 2 in one of those cells. And then I could make eliminations. Oh. Yeah, that's right.
Because we're imagining
Eliminations
that
on
given
those
9 is one of them.
Imagining the 9 is 2-5.
Yeah.
Yeah, so an ALS XZ wing is that. It's where 2 of the ends don't line up.
Okay, and you can still do some eliminations with that.
Yes. So what I called an ALSXZ ring, just to standardize because we're calling all of these things rings. You can also call it doubly linked. So it is a weak link on 1 and also a weak link on 2. So it's doubly linked. That's talking about the weak links.
Okay. Good name.
Yeah.
All right, so that was way more than I expected, actually. And I love how you connected everything together. I see you have 2 more tabs here. So what are those about?
Yeah, so these 2 tabs are puzzles that actually came together.
Nice.
So the first tab that I showed with the skyscraper or the X-wing, I took that idea and developed it into a full puzzle, and that's what you get here. That might give you some hint as what technique you might use. There is a skyscraper that you can use to solve this puzzle. There are also other techniques that you can use to solve this. There are multiples of them. So there, I think, are 4 different skyscrapers that you can find. There are 4 or 5 different 2-string kites. So have fun playing around with it. And then this one is the version of the ALS XZ ring that I actually got to work. Again, there are other things to find in this, but
yeah,
the focus is the ALS XZ.
So try to find the ALS XZ ring. Also try to say it. Very difficult.
It's hard to say.
Yeah. So in the description, there will be links to both of these puzzles, so you can try them out. They're, of course, classics, and they should, like Philip said, you might find a different way to solve them, but they do contain what we talked about here. So if you'd like to practice looking for those, these are some great puzzles to do so. And with that, I think this was a really great first episode. I learned quite a lot, and I feel like I hope you had fun explaining all that stuff to me.
I enjoy teaching.
It's obvious you put a lot of work into this, so I really appreciate that. And let us know in the comments if you enjoyed this. Hopefully you want to see more of these because we'd like to make more of them. Yeah, let us know how that goes. If you have not yet subscribed to my channel, please do subscribe so you can get more content like this. I also do live streams. I also do showcases of really interesting puzzles, classics and non-classics. So a lot of stuff for all kinds of different viewers. And by subscribing, you make sure you get that content. And it also it gets me closer to my goal. I just hit 500 subscribers, and I would like to hit 1,000. And that is not an arbitrary number. That is YouTube's number for considering me a real channel. So let's see if we can get me there. And
congratulations on 500. By the way.
Thank you. Yeah, I did not actually ever expect to get so many subscribers. But now that I have goals, I of course have to keep moving it, right? And I definitely thank you, Philip, for doing this with me. I know that you had to work around your busy schedule and making sure your kids were occupied during this recording and all that stuff.
Had to work around the kids being asleep.
Yeah,
basically it. Yeah.
And yeah, I'll definitely enjoy making more of these with you, and I always enjoy our conversations. So
thank you for suggesting it and for having me on.
Yeah, if you want to talk to us, we always hang out on the CTC Discord, community Discord. I also have my own Discord that we hang out in, where we always talk about theory and all sorts of crazy stuff. And Philip randomly posts PDFs of how to do exosets and set theory and things like that, which are always good reads. And he's posting all these difficult classics all the time. So that's awesome. And so yeah, I will see you guys next time.
Bye.